Sorry. Yeah, the Wednesday night video is tough. I just said that twice, so it must be true. Who are we missing tonight? Nobody. Do you like these? They're better frozen. Some things are just better cold, you know? Hmm? Yeah, I learned when I was about your age, a buddy of mine put a sack of them in the freezer. Yeah. I'm not your father. I thought you were extrapolating. I mean, I know there's some tendencies here. You didn't see that coming, right? Yeah, yeah, I'm sure you did. I'm sure you're going to come up to me in San Antonio and claim to be my long lost child dressed in rags or something like that. Okay, is everybody ready? Okay, tonight it's going to be incredible, stupendous, tremendous, and you'll like it too. Alex, pseudo steady state. You understand steady state. How can you have pseudo steady state? It's like steady state, but it's not. Like pseudoplastic fluids or pseudo relationships. I'm digging now. Eric, you're my foil tonight. Give me something with pseudo in it. Okay. What about my chemies? Pseudo reduced temperature and pressure? Why is it called pseudo reduced and not reduced? Because it's based on pseudocritical. Yes, it's based on pseudocritical, which is for mixtures. Anything else we use pseudo for? Sorry? Pseudoephedrine? That's like the base for meth? You mean? The other day in New Zealand, they found 100 kilograms of meth, and it was packed in the base of an umbrella stand, instead of cement. They packed it in there as that. I hate to mention this, but it came from China. We won't talk about that. Okay, so you said pseudo pressure. So pseudo pressure is not pressure, but it's like pressure. And pseudo time would be not time, but be like time. Okay. Any other pseudo things? Come on, Gabe. Pseudo new? Like the cars that you buy out there that said previously owned? Is that what you mean? Pseudo new? Okay. Math ladies, do you use pseudo for anything? No. Petrophysicist? No. Anybody else? Cameron, your mouth's full, so I can't call on you. I guess you'll just eat the rest of the hour. Yeah. I noticed that. Anybody else? Okay. So the concept is that it looks like steady state, but it changes with time, which is the whole point of steady state. It's not supposed to change with time. So how did that happen? Well, we assume certain conditions, and the condition is that, and sort of an explanation of this, steady state is that everything is constant within a certain distance. So what we do is we allow the distance to change with time, and we assume that that thing that was constant just magically stays constant. So it's pseudo steady state because it looks like it's steady state every time, but it's really changing with time. I don't think I did that justice, but we'll explain it, of course, when we derive it. And this is the start of where things really get interesting. Pseudo-steady state or boundary-dominated flow, well, okay, we have to go back to language. Do you remember when you were young and you used the wrong phrase and your teacher reminded you that you used the wrong phrase? No? Can you give us an example? Anybody? Joker? I'm sure you got beat a lot when you were a student. Yeah.
It's never for that. It's always for different.
For not being prepared, for being insolent, being rude, being immature. I haven't really gotten down the list yet, but I was just checking. Okay. I forgot where I was going with this. Okay. Pseudo steady state. Steady state means what? That there's a molecule by molecule replacement. The pressure at the outer edge, the pressure in the inner part, they stay the same, and the flux through the system, the volumetric flux through the system, is constant as well. Okay. So if we have something that changes with time, but it changes in a constant way, that would be the definition of pseudo-steady state. What's the thing that's constant, class? What do we always want to be constant? It makes life much easier. The flow rate, okay? The mass rate out of the system, or the volumetric rate out of the system converted to a pseudo-mass rate. See, I just said pseudo-mass, but converted to a mass rate using formation volume factors. So this assumes that the rate in the system is constant. Is there any system where the rate is constant? How many of you live in an apartment complex? Nobody. Okay, a few people. Is the rate of water coming into that from the water tower constant? There's a lot of it in the morning, maybe a little bit of it at night, and not so much. So your system, the rate varies, and the pressure in the system varies. Can you think of something that where you have to maintain a constant rate? Now the chemies are going to jump on this because you design your reactors where they have to have constant rates through them, but that's cheating. We don't really think about that. In our system, do we control the rate? No. Injection would be good, but even there you're going to have downtime, right? And even there you'll have maybe they didn't deliver the chemical right, or maybe they didn't deliver something else right. And it's a good point. I hadn't thought about injection, but in theory you could stay sort of constant on injection. That's a good one. Anybody else? No? Okay, so here our foundational assumption is that the rate in the system, the mass rate or the equivalent volume multiplied by formation volume factor, which gives you a mass equivalent, it will be constant. Now, why do I remember that? Okay. I want you to hold this. And I want you to hit me in the head if I say boundary dominated flow tonight. Boundary dominated flow. That wasn't really what I was hoping for, but thank you. All right, so I just said that the assumption that we're going to make is that the system is produced at a constant rate. What if instead the system is produced at a constant pressure? Okay. So we have two extremes, constant rate or constant pressure. Are the equations that govern that behavior the same? On an average mass basis, i.e. an average reservoir pressure basis, they essentially are. And we're going to show that tonight. So the next question is, if the extremes are constant rate and constant pressure, then everything else in between, is it valid for that? We'll see. So instead of saying pseudo-steady state, for anything other than constant rate, we say boundary dominated flow. Because the guy who beat me with a book was Dr. Lee. Every time I said pseudo-steady state, bang, he would whack me because you have to say constant rate. You have to think constant rate. Okay? All right, so we're going to derive all these relationships tonight, and it's not really as ugly as it seems, although it's not pretty. And we will move on. Okay, and then here's these versions. So now let's look at this for a second. Well, let's go back for just a second, actually. Sorry about that. So these relationships relate the pressure at the wellbore and the pressure at some distance into the reservoir. And if I can metaphorically hold my thumb over this, right here, and right here, is that the same as a steady state equation if those are 1? Remember we derived the steady state equations a few nights ago? So RE squared over RE squared minus RW squared, is that approximately 1? Of course. R squared minus RW squared over RE squared minus RW squared, is that approximately equal to 1? No. So there's a little bit of a hitch, but it is still sort of familiar. Okay. So it'd have to be that R squared over RE squared was approximately 1, but we'll come to that. So this, actually it is still right because we're scaling it, right? We're scaling the pressure in the system. We're moving across. But that first term is the one that really is tough. So we'll see. This, for all intents and purposes, this is the same as the steady state relationship we derived the other night, except for that funny term here. Okay. Now I forgot that we have to have this as our scaling term there, but that's okay. We'll deal with that. And of course, I added the skin factor. Why did I add the skin factor? Alex? Because anytime we're talking about wellbore pressures, we add the skin factor. Anytime we're talking about reservoir pressures, we don't have the skin factor. The skin factor only affects us where, class? At the wellbore. Okay? Next is some relationships with average reservoir pressure. What kind of average pressure is it? Is it time average pressure? No. Is it averaging apples over oranges? No. What is it? It's volumetric, but it's supposed to be mass average, correct? But we work in volume. So we assume, again, that we're working in reservoir volume, which is equivalent to mass units. So when we derive this, and we will in a little while, we will integrate pressure over distance and divide it by volume, and that'll give us the average reservoir pressure. Okay? Of course, we assume that that pressure over distance represents a volumetric average when we do that. Now we have a 3/4 instead of a 1/2. Recall we had a 1/2 when we derived the steady state equation. Now we have a 3/4. There's a slight difference. And then when we want to switch it to a general shape, we use a so-called shape factor, and this is Dietz's paper from the late 1950s. And what it is essentially a cheat. There's a special coefficient called a shape factor, which is valid at a certain point. So you could use any shape reservoir for this. Now, I told you the other day that they ask us what equations are the most important in petroleum engineering that they want to engrave in stone and put on a building. We probably are going to get 2 or 3, maybe 5 at the most, probably 4. That's one of them. You don't know it. But what's another name for well centered in a circular reservoir equation? It's also known as a productivity index equation. It's known as the deliverability equation. And we're going to derive that tonight. It's a biggie. It's a big night for petroleum engineers. Okay? All right. And then in order to add time, how do we add time to this? This is very simple. Who wants to take a guess? Anybody? Can? We're operating in PR or P bar, right? And we want to operate in PI. What relation that we use goes between PI and P bar? Material balance. So all we do is substitute in the material balance equation, and it in fact gives us that time dependency. Okay? So that's the Darcy units form, and then of course the field units form. Now that field units form could be used to estimate what? If you had pressure and time, what could that field units form be used for, class? What are the essential variables here? I'll give you a hint. This is one of them. Now, unfortunately, you're going to notice something. And what you're going to notice is there's permeability. Let me actually, come down to this equation. So now we're going to have a relationship in permeability and a relationship in skin factor and a relationship in terms of 3/4. Now I know all of you are saying, I don't care about 3/4, Tom. I know 3/4, but that's a shape factor. Okay. So that whole term is lumped into one thing. It has permeability, it has skin factor, and it has shape. Okay, if it's a circle, forget it, but nothing's ever really a circle. So there's 3 pieces of information that we want as results in one constant. That's the intercept term, right? How are we going to get it out? We're not. You can't. You cannot estimate permeability, skin factor, or the shape factor from pseudo-steady state data. Why? Because you get a blob, a lump parameter. How do you unbuckle a lump parameter? You have to have those pieces of information from somewhere else. And the somewhere else is from transient flow, we can estimate permeability, and from transient flow, we can estimate the skin factor. So if we had both of those, then we can estimate the shape. But again, that's for a later discussion. Suffice it to say tonight that that equation is the equation of a straight line. All that stuff that's kind of marked there, not the volume, but the other stuff is what? It's inside of a constant. We cannot get it out. Okay? The only thing we can estimate from pseudo-steady state flow is what? Reservoir volume. Okay? No pseudo-steady state, no volume. If we have pseudo-steady state, we can estimate volume. So what's this all the basis for? Ultimately, it's going to become the basis for RTA. Okay. And those of you who've studied this before may recognize that in order to perform RTA or type curve type analysis for production data, you must have transient flow data. Otherwise, you cannot estimate K and S. Okay. All right. So to begin with, we're going to assume that the pressure at all points in the reservoir changes at the same rate. Okay? How's that going to happen, class? I'll make it real simple. Everybody stand up. You didn't think you were going to get a gym class out of this, did you? All right? So when I'm at the wellbore, and you're distant from the wellbore. So during transient flow, the pressure drops at the wellbore, then what happens? And then what happens? And then what happens? Don't sit down. Okay? So that's what happens whenever the pressure drops here. There's a corresponding continuous pressure drop across the reservoir. At pseudo-steady state, what's going to happen? The pressure drops at the wellbore, and we all go down at the same time. Okay? I think you guys got it. Except for a couple of people like Ricardo. So, okay? You guys understand? The pressure at all points in the reservoir must change at the same rate. Now, this is crazy. How can the pressure at all points in the reservoir change at the same rate? Reservoirs are gigantic. How can this happen? Well, we must have had the pressure distribution reach the outer boundary, and the entire system is now in this decaying pressure syndrome, right? I think I need to take some of that late night medication on those low number TV channels to get my brain back in gear. Cameron's going, I've seen it happen before. They lose it in class. I can't put my words together perfectly here, but does everybody understand? The pressure at all points in the reservoir changes at the same rate. First thing we have to do is we have to have a pressure change relationship. dP bar dt. Who wants to volunteer for that? Gabe, where are we going to get dP bar dt? I say material balance. Very good. Okay. The next is we have to derive a relationship between average reservoir pressure and wellbore pressure. Okay, that seems like that's not going to be much fun, but we can do that. Anybody want to guess how we're going to do it? Mr. Liu? We're going to take the diffusivity equation and we're going to set that condition, the dP bar dt condition, on the right-hand side, and then we're going to integrate it twice. Now, the math ladies, this is really easy math, but conceptually, we got to think about this. We got to think really hard, because we're saying that what we're going to do is we're going to impose a condition on the relationship whereby a partial differential equation becomes an ordinary differential equation, and then all we have to do is integrate it twice. Okay. Ordinarily, partial differential equations require a lot more effort. We'll talk about that more in a little while. The next is to derive a pressure radius time relationship, and we'll talk about that. That's when we're going to add the material balance terms. So the first thing we do is we start with equation 2, which is a material balance for a slightly compressible liquid. Cameron, why did we choose a slightly compressible liquid? You want to pass it to Joker? That is the best answer I've heard all day. If you could only throw a couple of on the end of that. Anybody else? Mr. Sarkar, you want to take a shot, or you want to let Joker have it? Okay, come on, Joker. Oil is slightly compressible. Water is slightly compressible too, right?
Yeah, but not less slightly compressible.
Yeah, unless we fill it with gas like Topo Chico water. Okay, but okay, so we have an oil which is above the bubble point. It does not have gas evolved yet, but it is full of gas, and it has energy in it. Imagine a Coca-Cola that is completely filling the bottle, and you shake the daylights out of it, or maybe throw it on the ground. What's going to happen? It's going to spew, and so there's plenty of energy in there. We're going to release this energy slowly and in a controlled fashion. So the first thing we need to do is we need to write an expression for the oil in place. The oil in place is N. Its definition is what? Pore volume multiplied by saturation multiplied by formation volume factor. Okay? So the first thing we do is define that it's a cylindrical reservoir, and we're going ahead and substitute that particular relationship in. And so then, by the way, the saturation here is 100%. I failed to mention that, but oil, it's 100% oil saturation. And so we substitute equation 4 back into equation 3, and now we have a relationship that's almost sort of starting to look like something like a cylinder or something. Now we come back and we say, okay, the oil produced, the cumulative volume, NP, is the integral of the rate. So now we define dNP dt is equal to Q, and we substitute that in. So equation 8 is our starting point. It's Q multiplied by B divided by the porosity, the thickness, pi, RE squared minus RW squared. You got to take the little hole out of the donut. You could ignore RW squared if you wanted to, but we're not going to ignore that. And then we multiply it by the total compressibility of the system, which is the energy term. Everything in that relationship is constant, right? This is our whole basis. All right, so are we ready to go to the next slide? The next slide tells us what? There's a diffusivity equation. How many of you used to live in fear of the diffusivity equation? Yeah? You don't admit your hatreds. You like the diffusivity equation? You didn't admit your fear. Oh, it's not fear. You just don't like it. You don't care. Oh, you do care, but you don't like it. Okay. So we have an eventually honest man. Eric, you don't like it. Why? I'll, I'll be sure and mention that at dinner next week. Um, so I think I may have told you this, but whenever I went through the syllabus about 20 years ago, I had a geologist in the class ask me what the backward six was. And I told him the backward six was a free trip out of the class because we were going to be talking about a lot of backward sixes in here, more towards the end. It is a partial derivative. The assumptions of this are slightly compressible fluid, Cameron, our oil above the bubble point, constant fluid viscosity, single phase flow, gravity and capillary negligible, constant permeability, and in this case we'll say horizontal radial flow, i.e. there's no vertical component, there's no tangential component. If it was, then it would be different on the left-hand side. So now what we're going to do, take a deep breath. If the pressure at all points in the reservoir is changing at the same rate, then the average reservoir pressure is also changing at the same rate. We can make that deduction, right? So that's what we're saying with equation 10, is as long as the rate is constant, as long as our condition is that the pressure at all points in the reservoir is changing at the same rate, then we can approximate that partial derivative of pressure with respect to time with an ordinary derivative of average reservoir pressure with respect to time, and that changes the entire equation to an ordinary differential equation. Okay? So we began eliminating things, and our final relationship is equation 11. Equation 11 says 1 over r d by dr multiplied by the quantity, acting on the quantity r dp dr is equal to minus qb mu over phi kh. Sorry, I got to remember we're going to pull that pi out, and then re squared minus rw squared. Okay, so all that's constant. So now all we have to do is integrate this twice. Everybody's okay with that? So we separate and integrate twice. We're lazy, so the first thing we do is define a constant. That constant is equal to the right-hand side term, 1 over r d by dr acting on r dp dr, and then we have equals minus 1 over c. When we separate that and we can perform indefinite integration on it, we end up with equation 14, which is r dp dr equal to minus constant, right? It was minus, divided by 2 r squared, because the integral of r is r squared over 2, plus some constant of integration. Now we don't know what that is yet. We'll have to figure it out in a minute. Sorry. We're going to multiply through both sides by 1 over r in order to clarify it. So we have dp by dr is equal to minus c divided by 2 multiplied by r, c1, 1 over r. And we know that at the outer boundary, okay, the outer boundary, what's the pressure gradient at the outer boundary? It has to be 0. There's no flow. Remember, this is our assumption. The inner boundary condition is the rate is constant. The outer boundary condition is the rate's 0. Okay? So when we do that, something weird kind of happens. It eliminates one term, and so then we say, okay, looking at equation 15, if the left-hand side is equal to 0, then we solve for C1. C1 is equal to C divided by 2 RE squared. No problem. We'll substitute that back into equation 14 in just a second. There are occasions when there are boundedness conditions. In particular, whenever we're looking at 1 over r, a lot of times we're talking about r tending to 0 because we pretend that the wellbore is a line. And in that case, we have an unboundedness condition, and we'll talk about that when we derive the transient flow solution. But we have to make an adjustment for that. In this case, it was obvious that we had a situation where the gradient at the outer boundary was 0. So now we make that substitution. We extract the c over 2, and we now have re squared divided by r minus r. We again have dp dr, so we separate. What's going to happen? What is the integral of 1 over r, class? It'll be a logarithm, okay? So the first thing that happens is we integrate term by term. We again end up with r squared over 2, and now we end up with a natural log r evaluated from rw to art. and then we have the r squared over 2 evaluated from RW to R. So equation 19 represents our expression for the pressure, which is in anywhere in away from the wellbore all the way up to the outer boundary related to the wellbore pressure. So of course we substitute the value of C back into that. We do a little bit of rearranging, and we have equation 21. 21 is exactly the same as we would obtain if we were deriving the steady state form, but in this case it's actually a pseudo steady state form, and we'll talk about that some more in a minute. So now we have PR minus PWF is equal to some QB mu over 2 pi KH, which 2 pi again is the Darcy unit conversion. And then we have the RE squared divided by the RE squared minus RW squared. Natural log of R over RW. Again, that RE squared divided by RE squared minus RW squared is approximately equal to 1. And then we have our scaling with where we are in the system. Obviously, if that equation is evaluated at RE, that is equation 21, then that becomes exactly our steady state equation that we've talked about before. Now we have to derive the average reservoir pressure form. The average reservoir pressure in petroleum engineering is defined based on mass, the same as you would in chemical engineering, but unfortunately we work in volume. So we're saying that volume is a proxy for mass. Okay? If we're working in reservoir units, then volume and mass they're not the same obviously, but they're related by a constant, which would be density. Okay, so the definition is the average reservoir pressure for any radii is the integral from RW to R of the pressure evaluated over that particular volume, and then of course the bottom is just the volume. It's the integral RW to R dV. When we go on ahead and make those integrals, obviously the volume is just going to be 23, and then the dV is given there. So then we'll substitute the dV 24 back into 22, and when we do that, we have, as you can see, a whole bunch of things start canceling. Let me step over here. So we have a porosity term here. We have a porosity term here. We have a thickness term here. We have a thickness term here. We have a 2 pi here. We have a pi here. We have an r squared minus rw squared there. So this all reduces to this. And then we integrate our pressure over r, dr, pardon me. Now, we go back and we take equation 21, which is over here, and we just substitute equation 21 into this expression. I know I've repeated it here, but for the sake of argument, it's the same. And then we substitute this into here. Now, we could go through all the algebra, and I know you're going to be really thrilled with that, but you can see that you're going to have to integrate a logarithm. And the expression for integrating a logarithm will come along in just a moment. There's also an r here, so it's actually r log r over rw. Then there's an r cubed, and then there's an r. What's the integral of r, class? R squared over 2. What's the integral of r cubed? R to the 4th over 4, right? So what's next? What is the integral of r natural log r over rw? Well, you could just look it up in the book, but of course we do things the hard way around here. So we'll derive it by integration of parts, or integration by parts, and we work all that out. We have our expression given here. So our final form is equation 31. Okay. So the integral of r natural log r over rw works out to be an r squared natural log r and then an r squared here. So everything's going to work out just fine. It's a little bit ugly. So we have that term that I just mentioned. We have our 1 over 4 r to the 4th term. We have our 1/2 r squared term. We start working out all the algebra, reduce, 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 and we finally have this expression. So before we said that this particular term, re squared over re squared minus rw squared, is approximately 1. What is r squared divided by r squared minus rw squared? Approximately, class. It's approximately what? 1. Okay. If r is large enough. And then we have these terms over here. Now, if R is equal to RE, then this is 1/4. And if no matter what RW squared is there, that's a very small number divided by a very big number, it's going to go away. So just sort of as a guide, if we go on ahead and assume that RE squared, pardon me, divided by RE squared minus RW squared is approximately 1, RE squared plus RW squared divided by RE squared minus RW squared is approximately 1, and then RW squared divided by anything is approximately 0. What that does is it reduces this. Now, you'll notice that I stopped carrying the R because this is actually PRE. So this is evaluating this equation at the average, at the outer boundary. I have a little bit of a surprise for you to say that you can't really define the average reservoir pressure at a distance. You have to define the average reservoir pressure over the entire volume. The entire volume must be included in the mass balance. So I've sort of cheated here because I made up my own variable called P bar sub R. But yes, technically you can calculate the average reservoir pressure in a volume as it's changing. No problem. And in fact, I used that concept once to try to prove the drawdown volume, sort of like we'll talk about the radius investigation in a minute. But this is not the way you're really supposed to handle the average reservoir pressure. The average reservoir pressure, P bar, really implies the entire reservoir. So once we make those substitutions, we have minus 1/2, minus 1/4. See ya. And then we have, that comes out to be minus 3/4. Okay, so there's your, oh, he could have stayed if you wanted. Is he one of yours?
I know who he is.
Good. We'll give him a hug later and tell him, you know, don't be surprised if we show up at his house tonight. So this derivation of equation number 39, this is like, or 34, pardon me, this is the building block of production engineering. You may not like it. You may think, oh, this is silly, Tom. I can't believe we wasted an hour on this. But it's important that you recognize this is a building block of production engineering. And so then we have all this summary of equations. We don't have to go over that. Then there's a trick. And the trick is, at what location can you estimate P bar? Now this is stupid. Why, class? Because we don't know the pressure distribution in the reservoir anyway. But if we did, how could we estimate the average reservoir pressure? Well, we basically take one of the relationships, set it equal to 0, and it solves out. Does anybody want to guess? Is the answer a half? No. What is it? So if we take that value of R divided by RE, it's approximately 0.55. Okay. So just, there you go. So what? All right, now we're going to go back and we're going to use the material balance equation. We'll recast it into this form, which is the Darcy units form. We already saw this earlier. And what we're going to do is we're going to substitute this expression into equation 45, and that will give us the relationship for pressure, initial pressure, and all the other things. So this equation, again, we just derived. This equation is a material balance equation. So we're going to take and set this P bar into this term, and we're going to solve it, and it's going to give us equation 47. And equation 47 says what, class? It says that PI minus PWF, which is a pressure difference, if we wanted to plot that on a graph, is equal to this constant plus this constant multiplied by time. Okay? So this constant has permeability, and it has this 3/4 in it. It's also supposed to have the skin factor, which we'll come back and add later, but it doesn't in this particular form. I just assumed it was 0. But the important thing is to recognize that there's nothing you can do with this constant. It's just a big fat C or alpha or something else. But with this constant, the slope is inversely proportional to the volume. Okay. So again, we just keep rearranging, and then we have our final expression, And again, it doesn't really matter what the terms are. You're not going to separate them out. Okay. So sort of finalizing, I guess I would jump down here to either one of these field units equations. And in terms of field units, if you're working in days, you're going to have 5.615, which is the number of cubic feet per barrel. If you're working in hours, which is what we usually do in well test analysis, then you're going to have 24, or that number divided by 24, which is 0.23395. And again, this equation is absolutely valid for pseudo-steady state, but this constant that you're going to estimate, let's say you make a plot So Cameron, are you going to behave when you go to San Antonio? Did you already sign the form? Do you know what I was going to put on the form? That I will not pay bail. Do you guys understand what bail is? I don't know. You just got the look of somebody that needs bail money. Don't worry, Joker. I'm sure you'll be there too.
I promised my mom I won't go to jail.
Really?
In the USA.
Really? Have you been to jail in India?
No, that's another discussion.
Really? Why don't you give me a little heads up?
I won't ask you for bail money.
You will?
No, I won't.
Never?
I'm not in India.
I did. Oh, not in India? Thank you. That'd be ultimate long distance call. Just for me to tell you no. Okay, is this what it's supposed to look like, class? Sorry, I'm rubbing my eyeball here. That's what happens when you get old and tired. You guys didn't happen to see my daughter today, did you? She was around the office. Yesterday I bought a Monster and she drank it. It's tough having a daughter. Miss Wang, Miss Zhang, do you agree? Is it better to be a girl? Probably so, right? You can get away with murder with your father. So did I draw this correctly, class? Alex told me you guys were really good while I was gone. Thank you for that. You like dash lines? What's your favorite color, Mr. Sarkar? I bet you're a green. No? You guys hate graphical analysis, don't you? I think the computer should just do it all for you, right? Okay, so somebody tell me what I've just drawn. Did I draw this correctly? Why not?
The axis is going down. Especially
Yeah? You know what they say, you mess with the bull, you get the horns. How about now? Okay. Yeah. Okay, but that's not nice. That should be nice. I'll fix it. Mr. Liu and Joker, they got me. The old man drew it upside down. Hey man, it's hard being old. You don't believe me? Ask some other old person. Straight lines make up the universe. Now, did I understand correctly that Mr. Alex has not done special functions yet? He did Laplace transforms, right? But not special functions? Maybe I'll get them to do special functions this week. Oh, but you guys aren't leaving till Sunday, right? Yeah, because I have to be gone Friday and Saturday. Okay. Actually, I have to be gone Thursday, Friday, Saturday. So this slope M pseudo-steady state is equal to what, class? Is that right? What's the intercept? Thank you. You're very helpful. Okay, so it's 141.2 QB mu over KH times big constant. You guys like that? When you're old, you can cheat, but not when you're young. Okay? So what do we solve the big constant for? Well, actually, we can't solve for anything because we don't know permeability. Can you estimate RE? It's circular, right? But is it really circular? No, but is the reservoir circular? Yeah. There used to be a great cartoon that was, reservoir engineer's favorite shaped reservoir was a circle with a well perfectly in the center. Geologist's favorite reservoir was, this beautiful sand. Geophysicist reservoir was all crumpled up. I guess well logging, petrophysics, it's all one property. Can you use this concept? Where? How? Okay. Well, there has to be some mystery in life, so we'll continue. All right. So these are some plots that I made with a simulator back when I was a lot younger. So I built this simulator myself. It had about 1,000 circular cells or radial concentric cells. And what I was doing was I was generating constant rate profiles. This equation. What is this equation supposed to be, class? What's the equation of this line? Is it somewhere over in here? Is that the equation of that line? Yes, it is. Okay. And then when it rolls over, it no longer matches that equation, does it? No. We need to derive this entire equation. We'll do that later. We'll do that in one of the radial flow lectures. What is this 32.2 feet? The initial pressure is 4,800 psi. What is this 3,200 feet? Or 32.2 feet? Okay, what is it though? Say it louder. Okay, but is it real? Is that why it's off a little bit? So how do you derive that point of intersection, class? There's a couple of ways of doing it. One is to use the instantaneous line source solution. That's in Dr. Lee's book from 1980. Another is to use the continuous line source solution, which is called the probe radius formula, that you set equal to 0, and that's the intercept where it occurs. Okay? So the difference between all these formula are not the actual structure of the formula, but the constant out front, so it's approximate. Alex, is this a real distance? Is it real? Is there a point where the pressure goes to initial pressure? This is a fictitious point, right? Okay. You can't really solve where the pressure goes back to initial. Even if you use the line source, the full solution, it can't be solved. Okay. So each one of these has its own trend. And again, these are all, as Alex called them, radii of investigation. And what I've done is shown the formula. So is the formula conservative or liberal? Class? It's very conservative. Because that point of intersection should be back a little ways. It's a logarithmic scale even. Does it really matter? What would you use the radius investigation for? Anybody? Louder? Okay, that's a completely different thing. I agree with you conceptually, but that's a completely different thing. You're talking about the distance to an obstruction. This is a distance to a fictitious point where the pressure is equal to the initial pressure. We'll talk about that one some other time. Anybody? Sort of. At that moment. At that moment. How accurate do you think this has to be? Not at all. Right? Alex, you're going to design a well test. You're going to go to your supervisor. You're going to say, I want to design a well test that samples out to 100 feet. Okay? Why? Is that just a good number? Okay. What if you're on 40-acre spacing? What's the radius for 40-acre spacing, class? 748 feet. Sorry, could be meters, but okay. So what's 100 feet? That's nothing. Okay. But if you wanted to say, okay, how long do I have to flow this well before it reaches 748 feet? You could use the radius investigation formula to calculate approximately where that is. Okay. I told you guys this story, right? Kazakhstan story? I know I did. No? You remember? So I taught a short course in Kazakhstan. In Kazakhstan, they have to test, and when they test, they have to flare, and when they flare, they get fined. Go back to point number 1. They have to test. So they ran a test. They ran it for, I don't know, a month or something. They forgot to tell me that the oil looked like foamy shoe polish. So the viscosity of this stuff was like 1,000 centipoise. The permeability was like a Darcy. The compressibility of this stuff was also huge, foamy. Okay, so we ran the calculation, and the chief engineer, who was from Hungary, said, we're sampling several hundred meters into the formation. And I said, no, you're not. I calculated it, and it was 17 meters after after a month. I started to say 1,000 hours, but whatever it was. He went berserk, because we worked it out on the board, and he agreed with every number as I put it down. And then we made the calculation, and he just went insane, because all this time he had been telling management that it was sampling, 1,000 meters or whatever, and it was sampling 17 meters. So that is one use of the radius investigation equation. The constant out front is not going to be that far off. Okay. Now the next plot shows constant pressure case. Now remember, constant rate, constant pressure. Now all of these lines also conform to our steady state theory. Okay. But they progress, they propagate out into the reservoir. Alex, is this concept correct for constant pressure? Pretty much the same as we saw before, right? So approximately there, approximately there, approximately there, approximately there. Approximately. So the concept of propagation, is it rate dependent or not? No. So it does not matter, and this is going to happen. Some of you are going to be on remote location in some African country or some South American country or in the Middle East, and somebody's going to tell you that the propagation of pressure in the reservoir is a function of rate. Does this say it's a function of rate? No. This says it is not a function of rate. Now, there may be certain factors which are rate dependent, like the more drawdown you create, you have a problem, with gas blocking or asphaltenes or something like that, or some other element, but just raw diffusivity, no, it's not a function of rate. Okay. Now, what about pseudo-steady state? Pseudo-steady state says that the pressure at all points in the reservoir must do what? Must decline at the same rate. So if we take a slice of the reservoir pressure profile at different times, they should be parallel, correct? Are these parallel? Close enough. Okay, close enough. Now what's the next one going to be, class? This is the constant rate case. What's the next one going to be? Constant pressure. Are these parallel? Not exactly, but they're parallel enough. So the proof is that this concept is also valid for constant pressure. I realize this is induction, this is inspection, but conceptually, this concept is true for constant pressure as well. In fact, you can derive the expression that shows that, at least for wellbore behavior, it is the same. Okay? This is major accomplishments. Why? Because tonight we derived the equation for pressure in a bounded circular reservoir system. I know it's ideal, but we showed how it's supposed to behave. Can it be generalized to other shapes? Of course. Anything where all the boundaries are being felt is called boundary-dominated flow. If I'm the well right here, and this room, which is basically a rectangle, I start walking towards a boundary at diffusivity speed, the distribution's going to hit here first, right? And then it's going to hit there next. And then it's going to hit there next. And a long time from now, it's going to hit there. And an even longer time, it's going to hit back there, right? But once all ALL, the boundaries are being felt, what's the behavior? It will be pseudo-steady state. Okay. Now, how much of the life of a normal conventional reservoir, let's say permeability greater than 1 millirc, how much of the life of that well is going to be in pseudo-steady state? 99%. I need a hug. That's the perfect answer, okay? Now, when you drop the permeability by a factor of 1,000, how much of that reservoir performance is going to be in pseudo-steady state? Well, remarkably, it's probably still in the 90 percentile range. Why? Microdarcy reservoirs can achieve pseudo-steady state conditions after a year, maybe a little more. Depends on the configuration. You know, I have to admit. Actually, let me take that back. 0.01 millidarcies will do that, or sorry, 0.05 millidarcies after maybe 6 to 8 months, depending again on the properties, etc. I had a case from Mexico that I talked about maybe with you or not, but it was a well out in the middle of nowhere. They drilled a gas well. It's sort of mimicking what was going on in South Texas in the 1960s. And it's a portion of northern Mexico called the Burgos Basin. And the permeability was 0.001. Okay? It was in linear flow for 17 years. It went to boundary dominated flow at about 30 years. I had 45 years of data at that point. So that is a very long time. That's about 2/3, let's be generous and say half of its life is in pseudo-steady state, but the other half is in transient flow. Now let's drop the permeability another order of magnitude or another order of magnitude. How long are those wells going to be in transient flow? Basically, practically speaking, most if not all of their lives. So what is the response? You know, why learn about this if there aren't going to be any pseudo-steady state effects in unconventional reservoirs? Am I being too negative? Mr. Bate, when you look at your pressure distributions in your calculations, how long do you think it would take for a pressure distribution to propagate? Okay. But let me throw a number out there. They say, and they is people who model things, that it takes 30 years for a fluid particle to migrate 30 feet in a 1 nanodarcy rock. 30 years to move 30 feet in 1 nanodarcy rock. So where's all the oil and gas coming from, class? Anybody? No, but where is it coming from? How can you have thousands of barrels a day in production? Did I look like a windmill, you know, or maybe one of those kiddie planes about to take off? Where can it come from? And where is that? That's where we fractured it, correct? So right now, the only mechanism for producing unconventional reservoirs is hydraulic fracturing. Have there been hydraulic fracture treatments with more than 100 stages? Yes. Have there been hydraulic fracture treatments with more than 150 stages? That I don't know, but I'm sure it will happen soon. What's the longest horizontal multi-fracture well in the United States at this moment? Approximately. How long? 6,000. 19. Yeah. It was a Marsalis Utica well by Eclipse in Penn State. They're in State College. Yeah, I think they did. I don't know how effective it was. I mean, all of us think about that the far end doesn't get much. Also, when you start talking about almost 4 miles, right? That's a long way for fluid to move. I don't know where you live. I live about 10 miles from here. And That is a long way for fluid to move in a 5-inch or 4.5-inch liner or casing. Okay. I think Range Resources showed the other day that they've drilled 9 wells 15,000 feet or longer in the Marcellus. And there's,
Where that eclipse well was at.
I'd have to ask. Look it up and see. And it was reported 19,000. Maybe it's 18. I don't know. Yes.
So to
And you guys are right to get me back on track. This is what we're supposed to be talking
I'm
about.
sorry, I just had a
No, absolutely. This is the right thing to talk about.
so now I feel guilty. So what you're saying is when you have constant overpressure, your pressure profiles are still parallel, roughly.
Roughly. What I'm really saying is that boundary dominated flow applies to any shape,
And then
any configuration of rates, any configuration of rates.
okay.
Okay. So any shape, any configuration of rates, if you have boundary dominated flow. Now let me tell you the hard way of doing this. Okay. Every rate change causes a new transient. So if the system is at boundary dominated flow, every time you change the rate, in theory, that introduces a new transient. As long as the rate profile is primarily monotonic, those new transients are dwarfed by the boundary dominated flow behavior, by the pseudo steady state aspects of it. Okay. I can give you a paper to read.
Yes, please. Also, I mean, this might sound elementary, but even if so, they're parallel. Does that mean we can still use the equation that we?
Correct. Everything that we talked about tonight is valid as long as these pressure distributions are approximately parallel. Okay. Now I'll tell you a secret, guys. I know it's time for me to stop talking. But when I was your age, I derived what became RTA. I understand, I've told you that before. But my advisor took one look at this and said, "You've proved it." And I made a gazillion of these plots with all sorts of different rate profiles. I even made it random. You know, I figured out how to use a random number generator and just let it dance all over the place. But then when you plotted pressure drop divided by rate and cumulative production divided by rate, everything just worked out. Okay? And my advisor said, and I quote, "I'm not one to step on original thinking, Tom, but until you prove this analytically, I don't buy it." Not very motivating for a speech. Okay? So what did I do? How did I prove that it's valid for anything? I'll send everybody the paper. Okay? How would you do it? Sorry? I did run simulation. That wasn't good enough. I ran all sorts of different simulations. He wanted an analytic proof. How would you prove this analytically? You would have to take the analytical solution to this case, which includes transient, transition, and boundary dominated flow. And what would you have to do? You'd have to derive the superposition formula and then show that the terms are irrelevant. Okay? I'll send you the paper. You don't have to, I hope you don't have to write a report on it. So.
Is it the same paper?
Yes. Yeah. Okay, I better stop. Okay, so